Okay, in this video, we're going to go over chapter 3-5, and this is going to be talking about a few other diodes. So in this chapter, we'll start out with, it says several types of diodes that are less likely to be encountered as a technician, but are nevertheless important, are introduced. So it's going to show you several diodes here, but we're going to be looking at the laser diode, the Schottky diode, and the tunnel diode. So it has a few other ones here listed, but that's the ones that we're going to be going over in particular. Okay, so it starts out with the laser diode, and this is on page 148 of your text. And it says the term laser, and you need to know what this is. The term laser stands for light amplification by stimulated emission of radiation, as that is on a quiz. It says laser light is monochromatic, which means that it consists of a single color and not a mixture of colors, which is also something we've seen with LED. Laser light is also called coherent light, a single wavelength, as compared to incoherent light, which consists of a wide band of wavelengths. It says the laser diode normally emits coherent light, whereas the LED emits incoherent light. Because if you remember in the LED, it had more wavelengths, and those wavelengths in an LED is what controlled the color of the LED. Okay, so with this right here, that means that there's a single wavelength, which means one color, and it's considered coherent light. It says the laser diode, emits coherent light. LED is incoherent, and the symbols are as follows. So this here looks like an LED symbol, so it's the same symbol is used for the laser. So a couple of things you need to note about a laser, and we've seen PN junctions before. We've seen anodes, cathodes, all those types of things, and we've seen the depletion region, and you have the P in the inside here. Is that in a laser, you're going to see one side of the P is going to be highly reflective. The other end is going to be highly or partially reflective. So that's important as we get to talking here, because there is a reason, and it makes a big difference. And you can actually see as these arrows here, these are starting to move across the depletion region, and you can see that it's going to be reflected, and it's going to be going this way. So that's the reason why the highly reflective end and partially reflective comes into play. So that is the basic construction. Okay, it says the basic construction of a laser diode is shown, which we just went over. It says a PN junction is formed by two layers of doped gallium arsenide. The length of the PN junction bears a precise relationship with the wavelength of the light to be emitted. There is a highly reflective surface at one end of the PN junction and a partially reflective surface at the other end, forming a resonant cavity for the photons. External leads provide the anode and cathode connections. So here you have the external leads as considered axial leads. The basic operation is as follows. The laser diode is forward biased. So remember, this is a forward biased device by an external voltage source. As electrons move through the junction, recombination occurs just as in an ordinary diode. As electrons fall into holes to recombine, photons are released. A released photon can strike an atom, causing another photon to be released. And this is important because it's releasing photons now just by holes recombining, and then when that happens, photons are released. So that's kind of controlled, it sounds like. But then a photon can strike an atom, causing another photon to be released. So there's kind of a little avalanche effect here going on. So it says as the forward current is increased, more electrons enter the depletion region and cause more photons to be emitted. Eventually, some of the photons that are randomly drifting within the depletion region strike the reflected surfaces perpendicular. These reflected photons move along the depletion region, striking atoms and releasing additional photons due to the avalanche effect. This back and forth movement of photons increases as the generation of photons snowballs until a very intense beam of laser light is formed by the photons that pass through the partially reflective end of the p-n junction. So as you can see, one thing leads to another, and then it basically snowballs, like it says. That's the best way to describe it, until there is an intense beam of light, which, as it says, the partially reflective end. That's why it's depicted here, and then it allows the light to go out here. Right? Each photon produced in this process is identical to the other photons in energy level, phase relationship, and frequency. So a single wavelength of intense light emerges from the laser diode. Laser diodes have a threshold level of current above which the laser action occurs and below which the diode behaves essentially as an LED, emitting incoherent light. Okay, an application for a laser diode are the pickup system in your CD players. So that's what reads the disc. Said audio information is digitally recorded in stereo on the surface of a compact disc in the form of microscopic pits and flats. A lens arrangement focuses the laser beam from the diode onto the CD surface. As the CD rotates, the lens and beam follow the track under control of a servo motor. The laser light, which is altered by the pits and falls along the recorded track, is reflected back from the track through a lens and optical system to infrared photodiodes. The signal from the photodiodes is then used to reproduce the digitally recorded sound. Laser diodes are also used in laser printers and fiber optic systems. Okay, so that's the application. All right, so let's look at, let's go over a few things that we learned in this over a laser diode. Okay, we know that one, laser diode, laser stands for light amplification by stimulated emission of radiation. Okay. A laser is monochromatic. It has a single wavelength. We know that because it's coherent, right? So we go back to the text. So it says laser light is monochromatic, which means that it consists of a single color and not a mixture of colors. Laser light is also coherent, a single wavelength. Okay. So it has a single wavelength. Coherent light. Its construction has got a, let's do this right here, construction p-n junction is formed by two layers of doped gallium arsenide okay. It has a highly reflective surface one end of the p-n junction and a partially reflective surface at the other end. Okay. So basic operations. Basic operations. Forward biased by external voltage. Electrons move through p-n junction and recombination occurs. As electrons fall into holes, photons are released. A photon being released can strike an atom. So this right here is kind of going through the process of what we read in the text. So this right here would be some good notes to take. It says forward current increases, causing more electrons to enter depletion region and cause more photons to be emitted. Photons that are drifting in the depletion region strike the reflected surfaces perpendicularly, then the reflected photons continue striking atoms and releasing additional photons due to the avalanche effect. The back and forth movement continues until a very intense beam of laser light is formed by the photons that pass through the partially reflective end of the p-n junction. And as we've seen, an application is a CD player, which most of us should know what a CD player is. So this right here is just a kind of just so we can kind of review of what we've went over so far about the laser diode. So this right here is some of the things that you'll need to know about a laser diode. So the next one we're going to be talking about is a Schottky diode. Okay. So let's go to a Schottky diode in the text. Okay, Schottky diodes are high current diodes, used primarily in high frequency and fast switching applications. They are also known as hot carrier diodes. The term hot carrier is derived from the higher energy level of electrons in the N region compared to those in the metal region. A Schottky diode symbol is shown in figure 349. So this right here is just one of the, this is the symbol for this one. I was thinking about a tunnel diode because there's like 3 different symbols primarily for a tunnel diode. So this is the symbol for a Schottky. Okay, a Schottky diode is formed by joining a doped semiconductor region, usually an N-type, with a metal such as gold, silver, or platinum. Rather than a p-n junction, there is a metal semiconductor junction as shown in figure 350. So here's the construction. The forward voltage drop is typically around 0.3 volts because there is no depletion region as in a p-n junction diode. Okay, so still have the cathode, anode, and the anode is connected to the metal region. Again, the cathode has got the N region. Metal semiconductor junction. So this is not our typical diode. So the Schottky diode operates only with majority carriers. There are no minority carriers and thus no reverse leakage current as in other types of diodes. The metal region is heavily occupied with conduction band electrons and the N-type semiconductor region is lightly doped. Okay, so this area here is lightly doped. When forward biased, the higher energy electrons in the N region are injected into the metal region where they give up their excess energy very rapidly. Since there are no minority carriers, as in a conventional rectifier diode, there is a very rapid response to a change in bias. The Schottky is a fast switching diode and most of its applications make use of this property. It can be used in high frequency applications and in many digital circuits to decrease switching times. The LS family of TTL logic stands for lower power Schottky, is one type of digital integrated circuit that uses the Schottky. Okay. So let's talk about a few things about a Schottky. Okay, a Schottky diode. It's a high current diode used in high frequency, fast switching applications. It's formed by joining a doped semiconductor region, which is usually N, with a metal, which is normally gold, silver, or platinum. It has a metal to semiconductor junction. VF is 0.3 for forward biasing voltage is 0.3. It operates with majority carriers only. And it has no leakage current. Okay. And with that, we've seen that this right here is a typical symbol for a Schottky diode. All right. So the last one we're going to be going over is a tunnel diode. And that is starts at the bottom of page 150 in the text. And here's two symbols of a tunnel diode. And you also see a third one where it looks like this without the circle around it. So you may see one without a circle. So just FYI, just making sure that you know that. But it says the tunnel diode exhibits a special characteristic known as negative resistance. This feature makes it useful in oscillator and microwave amplifier applications. Two alternate symbols are shown in figure 3-53, which is here. Tunnel diodes are constructed with germanium or gallium arsenide by doping the P and N regions much more heavily than in a conventional rectifier diode. This heavy doping results in an extremely narrow depletion region. The heavy doping allows conduction for all reverse voltages so that there is no breakdown effect as with the conventional rectifier diode. This is shown in figure 354. Which is here. So the characteristic curve is different than in a regular rectifier diode. Okay. It says also the extremely narrow depletion region permits electrons to tunnel through the p-n junction at very low forward bias voltages. The diode acts as a conductor. This is shown in figure 354. Between points A and B, at point B, the forward voltage begins to develop a barrier and the current begins to decrease as the forward voltage continues to increase. This is negative resistance region. This effect is opposite to that described in Ohm's law, where an increase in voltage results in an increase in current. At point C, the diode begins to act as a conventional forward bias diode. Okay. So this right here is what it's saying, is that as you increase VF, which is the forward bias voltage, you start increasing current. But when you get to a certain point, it's going to start going back down. And then when it finally gets to this point of the VF, the current's going to start going back up. So it doesn't react as a conventional rectifier diode does. Because right here, you've got forward bias voltages, just you don't have a lot of forward bias voltage, but you have you've got these where it says here, let me get back to that, where it allows electrons to tunnel through the p-n junction at a very low forward bias voltage, and the diode acts as a conductor. So what that means is between that point A and B, we have this tunneling effect, right? So it's acting just like a conductor. So you have forward bias voltage is very low, but we have current going up. But as at that point B, the forward voltage begins to develop a barrier, and the current begins to decrease as the forward voltage continues to increase. And it says this is the negative resistance region. So what it's saying is that once it gets to this area here, you start getting that negative resistance, and it starts going back down. And then at this point is where it actually starts activating and starts working. So here you have this tunneling effect going on. That's why it's called tunneling current. It gets to this point, you reach the negative resistance, and then it's going to start going down as voltage increases. Then when it gets to this point, it's going to actually start, current's going to start rising again, and it's going to start acting as a regular rectifier diode would at this point. All right. So an application is a parallel resonant circuit. Can be represented by capacitance, inductance, and resistance in parallel. It says in the parallel equivalent of the series winding resistance of the coil. So basically what we're looking at here, it's easier just to show you this, is that without a tunnel diode, you're going to see this right here happening in an oscillator. And it's going to basically start out and just kind of start going down like this. But if we put a tunnel diode in, then it's going to keep that oscillation the same all the way through. See how here it kind of goes down? Here it stays true. So that's what the tunnel diode will do for us in a circuit. Now, we don't have any circuits that we would do in class, but this is something that you would use in an oscillator. Okay? So I believe that's it for that. Those three diodes, just make sure you know the symbols. Make sure you know an application for each. Take the notes that we have on each one, and you'll have a quiz on this right here shortly. So thank you for listening.